So now we come to integration by parts. One of the funnest integration techniques out there for everybody that I've ever known. And it makes use first by remembering how we find the derivative of a product of functions. So suppose I want the derivative with respect to x of u times v, where u is a function in x and v is also a function in x. Well, remember the product rule. The derivative of the first, so I would have du with respect to x times the second as is, right? The derivative of the first times the second as is plus the reverse. The derivative of the second, dv with respect to x times u, just using the product rule. Well, we can then convert this to a differential equation by noticing that we have the same denominator across an equal sign, which means they can cancel, and I'm left with derivative of u times v equals du times v plus dv times u. Or written in the more customary way, the derivative of u times v equals v du plus u dv. Now I integrate both sides and I get the antiderivative of the derivative of uv is just uv, and separating the two functions I get the antiderivative of v with respect to u, so v du, plus the antiderivative of u dv. And finally, a little bit of algebraic manipulation. I get the antiderivative of u dv equals uv minus the antiderivative of v du. All I did was subtract the integral of v du to the other side and rearrange it around the equal sign. And this is the formula you want to memorize for working with integration by parts. And remember, if you listened carefully just a second ago, you heard me say memorize. This is one of those formulas you have to know, that the antiderivative of u dv equals uv minus the antiderivative or the integral of v du. Must be memorized. So finally, at long last, we've come up with a way to integrate when there is a product, which is fabulous. We're going to do a double substitution. We'll be substituting a u and substituting for a v to make it fit the formula, whatever function we're given. Sadly, the best substitution to make is not always instantly obvious. So let's look at an example. I'll do it two ways, and one will be perfect and the other not so perfect, and hopefully we'll be able to call out of that some understanding about the right choice. So let's look at finding the antiderivative of x e to the x dx. And of course, we're definitely looking at a product of x and e to the x. And we want to do, as I mentioned before, a double substitution, but we're not going to do it as directly as you might be used to. In one case, we want to choose something to equal u. And in this case, I'm going to choose x to equal u. And then we want to choose a different value, or the rest of the problem, to be dv. So I've got a u and a dv. When I make that substitution, if u equals x and dv equals e to the x dx, I have to first find out, this part's easy, take the derivative of u, so I get du equals dx, right? 1x times dx. Now, working backward from dv, and this is the place where you want to show a lot of caution, because especially when you're new at this, and even when you're not new at this, it's super easy to work backward in the wrong way. We want to take the antiderivative, because what we want to do is get to v, and so I need the antiderivative of this side, which means also the antiderivative of this side. And when I take the antiderivative of v, I just get e to the x. Working forward to be sure I've done it correctly, if v equals e to the x, what does dv equal? E to the x dx. Done. Now I have all of my uv, du, and dv's just to plug into this formula. So the antiderivative of x, e to the x dx, that's this first side, equals u times v, u is x, times v, e to the x, minus the antiderivative of v, e to the x, du. And what is du? Just dx. And what's happened is I've come close enough now where I can just take the antiderivative here. I already did it once, so I know that equals x e to the x minus the antiderivative of e to the x is e to the x plus c, and I'm done. Now, you can probably imagine that this is the proper substitution because this all went so beautifully for us. Let's look at the example when it's the wrong substitution. This time I'm going to use the opposite substitution for u and v. So if the problem is antiderivative x e to the x dx, the substitution I want to use this time is I'm going to let u equal e to the x and dv equal x d to the x, or x dx. Then differentiating u, I get du equals e to the x dx, and v, working backward, anti-differentiating, I get x squared over 2 for v. Now when I plug it all back in, u times v, x squared over 2 times u, e to the x, minus the antiderivative of v, x squared over 2 du, e to the x dx. So we can see that this got more complicated than in the beginning. So I started with x e to the x dx. There's nothing wrong with this, except I've just made something even worse. And if this was hard to find the antiderivative of, this certainly is. Or actually, I just ended up with exactly the same thing. And there's kind of a cool step you can use to resolve yourself out of this that we'll talk about in a little while. But that's not the point. The point I'm trying to make is you don't want to do a substitution. Generally, you want this step to make it to go from something complicated to something less complicated. If you go from something less complicated to something more complicated, you're probably making the wrong substitution. Let's do another example. This time we're going to use a natural log. We want to integrate the natural log of x dx. Now in this case, there's not really a wrong substitution because you only have one substitution choice. The only thing that you can possibly let u equal is the natural log of x. And so dx or dv has to be dx. So v has to equal x, and du has to equal 1 over x dx, which we learned in our last lesson. Now I can start to put it together using the formula. This is the left-hand side. So u times v, so I have natural log of x times x natural log of x, minus I want the antiderivative of v du. So v is x over x dx. X natural log of x minus the antiderivative of 1 dx, but that's just x natural log x minus x, the antiderivative of 1, plus c. All right, so let's do another example. I want to integrate e to the x times the sine of x dx. Okay, that's a little scary, but really it's just a product, right? All I have is a multiplication right here, e to the x times sine, e to the x times sine x, just a product. So I'm going to do a simple substitution, or excuse me, a uv substitution. So I have u, I'm going to let be e to the x, and dv, I think I might have said v here, u is going to be e to the x, and dv is going to be sine x. So if I differentiate or take the antiderivative of sine x, I get v equals negative cos x. And going forward, differentiating u, I get du equals e to the x dx. So now I put it all together using my formula, and I have u times v, so I have negative e to the x cos x minus v du. V is a negative cos x, so it's going to be plus the antiderivative of v du. So I'm going to put the e to the x first, then the cos x. Remember, it's not a minus cos x because I distributed or I factored that out. And dx. Okay, done, almost, except look what happened. I didn't make it easier. I just ended up with something out here and then exactly the same thing in here except a different trig function, but it looks almost identical. When that happens, it's actually kind of good news because it tells you you're on the right track. All you have to do is integrate by parts one more time. So again, we're going to take u and let that equal e to the x, and then dv, this time is going to be cos x dx. Oh, I should have put a dx there. Cos x dx. Now differentiate u to get du, e to the x dx, and integrate dv to get v equals positive sine x. Now I'm going to write the formula again. I have to keep this, negative e to the x cos x plus, now this part says that I have to do the same thing using the by parts all by itself. So that gives me uv, writing it in the same way again, e to the x sine x minus the antiderivative of v du, sine x e to the x dx. So I know what you're thinking. You're thinking that you're just going in circles and I'm taking you there, and it's very frustrating and dizzying. But no, it's not, because look what happens. I ended up right back where I started, which means this side of the equation has e to the x sine x dx on it over here, and I've got a negative one over here. So if I add this to both sides, I'm going to have two of them on this side. Did you see that? If I add the antiderivative of e to the x sine x dx plus the antiderivative of e to the x sine x dx, that just means I have two antiderivative e to the x sine x dx. That's easy enough to do because all I have to do now is divide both sides by 2. This one disappears, and I'm right back where I started. The original problem is equal to all of this divided by 2 with one small critical change, and let me go ahead and rewrite it before I do that. E to the x cos x plus e to the x sine x, all divided by 2 plus c. Now, in this process where you integrate by parts twice, the one thing you have to be careful of is that the second integration by parts doesn't undo the first one and take you right back where you were. Even if it looks a little bit more complicated, in the process, you'll just end up back where you were. So you pretty much want to mirror the same process for your first substitutions the second time. If I had substituted in this second substitution, if I had let u equal the cos x and v and dv equal the ex dx, what would have happened is I would have undone and just ended up right back where I started. Let's do another example because we're having so much fun. I don't really want to stop yet. Let's do the antiderivative of x times the square root x plus 1 dx. So this is a little bit more complicated, but if you look at it, it's just a product, x times some other function of x. One function of x times another function of x. Now, if I craftily choose my substitutions, I think I'll be good. So I'm going to let u equal x, and dv has to equal all the rest of this. I'm going to rewrite it as x plus 1 to the 1/2 dx. So I've taken this is u, and I've let this whole thing equal dv. Now if I calculate backward and forward, well, du just equals dx in this case. And v, taking the antiderivative, gives me 2/3 times 1 plus x, I just rearranged it, 3 to the 3/2. All right, let's do our substitution. I'm going to write it down again. So if I'm looking for the integral of u dv, that equals u times v minus the antiderivative of v du. So now I can use this side to substitute these values, and I have u times v is x times 1 plus x to the 3/2. Darn it, I thought I left a little room here, but I didn't. So it's 2 times all of this, all divided by 3. Probably could have written that a little bit neater, but we'll clean that all up at the end if I need to, minus the antiderivative of v, which is 2/3 times 1 plus x to the 3/2 du, which is dx. So I think I'm going to rewrite this. I think I'll write 2x over 3, so 2/3 x times 1 plus x to the 3/2 minus constant multiple, right? 2/3 times the antiderivative, x plus 1, oh, I don't know why I keep switching those back and forth. It's okay, it doesn't hurt anything, dx. Now this is a simple substitution. I'm going to let u equal x plus 1, and so du equals dx. 2x over 3 times x plus 1 to the 3/2 minus 2/3 times the antiderivative of u to the 3/2. This time dx just equals du. And now take the antiderivative here, and I get 2x over 3 times x plus 1 to the 3/2 minus 2/3. Well, the antiderivative of u to the 3/2 is u to the 3/2 plus 1 is 5/2 over 5/2, which is 2/5, plus c because I've taken the antiderivative. And now I think I can clean the rest of it all up in one fell swoop. 2x over 3 times x plus 1 to the 3/2 minus 2/3 times 2/5 is 4/15 times, well, u is x plus 1 to the 5/2, and I don't think I need this paren, plus c. So there we go, one more tool in our arsenal for anti-differentiation, integration by parts.